As a specific note about that, the typical 1,000-gallon concrete grease interceptor is a traditional setup with baffles and inlet piping that comes down in a dip tube fashion. Probably all very familiar with it. It stems from the septic tank design, and the 1,000-gallon concrete precast concrete interceptor meets all of these standards, but the question is it an efficient separator? And we're finding more and more with our own field data as we ask pumper contractors and installing engineers and pre-treatment directors from municipalities, are these doing the base function of separating grease efficiently and keeping the effluent quality on the outside of the interceptor good? And the answer is, in a lot of cases, no. And we're going to get into why that's happening, but the point here, the takeaway from this, is that these standards have no criteria for efficiency. They're just design standards, and they don't get really to the nuts and bolts of why have a grease interceptor in the first place. So there's been some recent feedback that we've been doing some tests in various municipalities, and we have parts per million data, which parts per million or milligrams per liter is an efficiency standard of the F.O.G content in the effluent wastewater stream. And we're finding that with different designs, we can achieve equal or better effluent quality as far as parts per million of grease in smaller footprint interceptors as very large grease interceptors. And the point there is that by engineering the inside, or the guts, so to speak, of the interceptor to have a better flow pattern, to better use that liquid volume inside of there, you don't need a massive footprint, and you don't need all of that water volume inside the unit to get that good effluent quality.
So just sort of a digest of what we just talked about for performance-based standards versus design-based standards. There are 3 performance-based standards on the market right now, and then there are 3 model codes: the Uniform Plumbing Code, the IPC, and the National Standards Plumbing Code, that all sort of require the same standards. There's a large overlap throughout different regions of the country where they're asking for the same thing in a different language. And then the same issue arises with the design-based standards, that there's a large overlap there as well. So you might go to one municipality and an inspector might ask you, is that PDI approved? You could say, no, it's ASME certified, and they're not familiar with the nomenclature, and they might not think that it's a suitable product. So what's the problem with having multiple codes that do the same thing? Just to kind of touch on that one last time, there's different groups having jurisdictional authority over local grease code enforcement, often more than one of those groups having duplicitous jurisdiction in the same municipality. So the plumbing inspector, the health department, the industrial pretreatment office, F.O.G-specific offices, all people that are involved in the inspections of a job site that are kind of asking for the same thing, or in some situations aren't even in cahoots with each other, and they're asking for slightly different things. And this just creates an overall code climate that's not conducive to the consideration of new and emerging technology. When you've got a bogged down bureaucratic process, it can basically stifle innovation as we see it. So we think that there's definitely room for a lot of these standards to streamline, come together, start talking to each other, and then create some more logical requirements for these products. They don't have to be huge elephant caskets as far as grease interceptors are concerned. There are technologies that are out there that are proven that a smaller footprint product can accomplish the same grease storage capacity and efficiency and save maintenance costs as well.
So at this point, we're going to get a little bit more into the nuts and bolts of how a grease interceptor works. There are 3 tenets of efficient grease separation: flow control, flow pattern, and retention time. And really, you can make an argument for any one of those 3 as being the most important. And the takeaway is that the way those 3 are used in any given interceptor design is going to have a direct impact on its efficiency as far as a separator. Some units might do a better job of having an engineered flow pattern, but might have less retention time and do a better job of separating, and that might be the reverse for another unit. So the key is that those 3 work in concert in an efficient way to ultimately separate the grease. Flow control, as Charlie pointed out, in a PDI standard, which has been around for 60 plus years, has always been an external flow control T. It's something that's on the inlet side of the unit. Make sure you guys are all on the right slide here. It's on the inlet side of the unit, and basically what it is it's a fancy name for a throttle on a plumbing line. It's a smaller orifice. It slows the water down before it gets to the grease interceptor, because quickly moving water is bad for separation. Number one, it keeps fats, oils, and grease, or F.O.G, and food sediments entrained in the flow path, and ultimately that can lead to grease going out the outlet line, which you don't want. So that's the main reason for flow control, to slow the water down. The external flow control design, as you can see in the picture on the slide there, is, again, it's a T that's on the inlet side. It has a vent, which is not really a vent, but it's an air intake, actually. And the theory is that as the water moves from the bigger ID, the internal diameter of the pipe, to the smaller ID of that flow control orifice, that it accelerates, and on the other side of that flow control orifice, it actually creates a suction or a negative pressure and pulls air down into the effluent path, or I should say the influent path, in air bubbles, and entrains those air bubbles into that moving water going into the unit, and those air bubbles help the grease separate inside the unit. That is the theoretical design behind an external flow control T. There are some inherent problems with external flow control. The main one, far and away, and again, this comes from questioning contractors, pumper contractors, as well as plumbing installers, and commercial kitchen staff, is that they clog. Anytime you have a throttle that small in a food waste line, it's going to clog with food and grease and debris. And when it does, it has to be easy to clean. And a hard piped in external flow control is very hard to keep clean consistently. So what happens? Well, they get uninstalled, pretty much. And when they get uninstalled, the greasy water is moving through there too fast, and you've kind of undermined the design of the unit. The second type of flow control is internal or built-in flow control. Charlie touched on that. The ASME grease interceptor standard was the first one to allow for other types of flow control. And so there are designs out there, including the Schier design, that uses built-in flow control. You can see it right here. This is our inlet diffuser with the built-in flow control. And the main thing behind built-in flow control is that it's readily accessible, number one. So when it clogs, because it's not a matter of if, but when, it's readily accessible to be easily cleaned out and reinstalled. So that's number one. It also doesn't have an air intake, you'll notice. The built-in flow control design, by its own definition, does not have an air intake. So it literally is just slowing water down as it comes into the unit.